Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to this BSc Semester 1 of BSc Honours Chemistry course. And in this course, in the first module, we have discussed about the atomic structure, and in the second module, we are discussing about the periodic properties of the elements. In the first lecture of periodic properties, we have discussed about the periodic trend of certain periodic properties like the effective nuclear charge, the atomic radius. Now in this lecture we will discuss about some other periodic properties. This is Professor Ravin Zugade from Department of Chemistry, Rashtrasant Tukadoji Maharaj, Nagpur University, and the lecture has been prepared under the academic expertise of Professor L.J. Paliwal. Outline of this lecture is: we will discuss about ionization enthalpy. What are the factors affecting ionization enthalpy? Variation of ionization enthalpy in periodic table. Then electron gain enthalpy, the factors affecting it. And in the end, we will discuss about variation of electron gain enthalpy in the periodic table, that is across the period and down the group. Let us start with the first concept of ionization enthalpy. Ionization enthalpy or ionization potential. Ionization enthalpy is defined as the minimum energy required to remove outermost electron from isolated gaseous atom in its ground state. This is ionization energy or ionization enthalpy. Both the words mean the same. And since it is an energy, it is expressed in terms of kilojoule per mole of an atom. The word potential has come from a different phenomena or different experiment where the minimum potential difference required to apply to discharge tube in order to remove the most loosely bound electron from isolated gaseous atom, and this is called as ionization potential. It is generally expressed in electron volt per atom or electron volt per mole. Now both of them are unanimously used and meaning the same. Sometimes we use the word ionization enthalpy, sometimes we use the word ionization potential. Both of them mean the same. Now consider an atom consisting of a few electrons or 2 electrons in the first shell, a few electrons in the second shell, a few electrons in the third shell. If we know that every electron is bound by the nuclear force of attraction, and consider this particular electron, it is definitely under the influence of attractive force from the nucleus. Now if I want to remove this electron, because ionization enthalpy is nothing but the energy required to remove the outermost electron. Now these 3 electrons are the valence shell electrons. So if I want to remove the electron, definitely the electron which is outermost will require the minimum energy. The electrons inside, they will require much higher energy. So if I want to remove this particular electron, I will have to supply certain energy so that this energy should exceed the attractive force between the electron and the nucleus. And when this energy is supplied to the electron is expelled out of the atom. But at the same time, there is a positive charge generation on the atom, because now the atom is not electrically neutral, because the nuclear charges are same, but the one electron is less. As a result, the overall atom gets positive charge, and what we call it as a cation, with a monovalent cation or with one positive charge. Now it is possible to remove one more electron from here. I will have to supply some energy in order to remove one more electron. let the energy is E2. So if an energy equal to E2, which is greater than the attractive force between the nucleus and this electron, if I supply it, the electron will absorb this energy and will be expelled out. But at the same time, one more positive charge will be formed on the atom. So now the atom is not a neutral atom, not a monovalent ion, but it is now a divalent ion. So there are two positive charges on this particular ion. I want to remove one more electron from the valence shell. So I supply an energy equal to E3. When we supply this energy, the electron absorbs this energy and it is expelled out, forming a tri-positive ion. Now we have removed the electrons successively. So first electron is removed. The energy required to remove the first electron is called as first ionization enthalpy. The energy required to remove second electron is called as second ionization enthalpy. And the energy required to remove the third electron, that is called as third ionization enthalpy, and so on. So we can have n number of ionization enthalpies. Now let us see what are the factors which govern the ionization enthalpy, or the factors which influence the ionization enthalpy in a periodic table. The first factor is the atomic size. Second factor, the nuclear charge. Third one, the screening effect. Fourth one, the penetration effect. And fifth one is the electronic configuration of the atom. We will discuss all of these factors one by one and their influence on the ionization enthalpy. Let us start with the first factor, that is atomic size. Now, consider an atom having smaller size and another atom having the same nuclear charge but a larger size. Now, if we consider these two atoms and having electrons in the valence shell. Now, since in the first atom the distance between the electron and the nucleus is less, the force of attraction is large. As a result, if we want to remove this particular electron from this smaller atom, then the force of attraction, or it is under the influence of smaller force. But if we want to remove an electron from a larger atom, it is under the influence of the nuclear force to a lesser extent, because we know that the electrostatic force of attraction is inversely proportional to distance between the two charges. Hence, this force is larger, this force is smaller. As a result, the energy required to remove the electron from the smaller atom is more, whereas the energy required to remove the larger atom or electron from the larger atom is less. In other words, we can say that smaller is the atom, more is the energy required to remove, larger is the atom, less is the energy required to remove the electron. That is, the ionization enthalpy is inversely proportional to atomic size. Smaller is the size, more is the ionization enthalpy. Second factor is the nuclear charge. Now consider again two atoms having same size but one with a higher charge or larger charge and second with a smaller charge. So two atoms, one with a smaller charge, smaller positive charge in the nucleus, or the nuclear charge is less. In second case, the nuclear charge is more. Consider that the atomic size is same in both the cases. Now in that case, it is quite obvious that the force of attraction between the nucleus and the electron will be proportional to the charges, or that is directly proportional to charge. In other words, we can say that if the charge on the nucleus is more, the force of attraction between the nucleus and the electron is more. That is, electron is under the influence of the nuclear force or a stronger nuclear force if the charge on the nucleus is higher. Hence, less energy is required if the charge on the nucleus is small or less, and more energy is required to remove the electron if the nuclear charge is more. That is, the ionization enthalpy is directly proportional to nuclear charge. That is, if the atomic number goes on increasing, definitely the nuclear charge goes on increasing, and hence ionization enthalpy should go on increasing. The third factor which affects the ionization enthalpy is the screening effect. Now we know that what is screening effect. Screening effect is the reduction in the nuclear force of attraction experienced by a particular electron because of the intervening electrons or the electrons present in between the nucleus and the outermost shell. So these electrons definitely reduce the effective nuclear charge that we call as Z effective, and we have discussed in atomic structure that this screening effect is given by screening constant, which can be calculated by using the Slater's rule, and the effective nuclear charge is taken as the actual nuclear charge minus the screening constant. Consider two atoms, one where there is only one shell and second atom where there are two shells. Now if we want to remove the electron from this particular atom, it is directly under the influence of the nuclear force, and hence the force of attraction between the nucleus and the electron is higher. This is quite obvious because the force of attraction experienced by the nucleus, by the electron due to the nucleus is larger, or what we call as effective nuclear charge is more. Whereas in the second case, the attractive force experienced by this particular electron is less, even if the actual nuclear charge is same in both the cases, but due to these two electrons which are present between the outermost electron and the nucleus, the force of attraction gets reduced. As a result, what we call as the effective nuclear charge experienced by the outermost electron is reduced. As a result, the force of attraction decreases. In such case, more energy is required if the effective nuclear charge is more, and less energy is required if the effective nuclear charge is less. In other words, we can say that ionization enthalpy, which is the amount of energy required to remove the outermost electron, is inversely proportional to screening effect or screening constant. Next factor is the penetration effect. Now this penetration corresponds to the electron charge density of a particular orbital. We know that we have discussed this particular diagram of probability distribution curves of various orbitals like 1s orbital, 2s orbital, 2p orbital, 3s, 3p, 3d orbitals. Now if we observe them carefully, we will find that the s orbitals have some small charge density near the nucleus. Consider this 1s, 2s and 3s orbitals. Now this 1s has maximum electron charge density very close to nucleus. Similarly, 2s orbital has got some charge density near the nucleus. Same is the case with 3s orbital. Even if the maximum electron charge density is shifting away from the nucleus, but still some electron probability is very close to nucleus. Such effect is called as penetration effect. When we come to 3p, now consider 3s, 3p and 3d. Now 3s orbital has some electron charge density close to the nucleus. 3p also has got some electron charge density, but it is not as close to the nucleus as 3s. But 3d has negligible electron charge density close to the nucleus. In other words, we can say that 3s orbital is most penetrating and 3d is the least penetrating among the three. Hence, this penetration effect follows the order S greater than P greater than D greater than F. It means that if an electron is present in S orbital of any shell, it will experience greater force of attraction from the nucleus because it is more penetrating towards the nucleus. Hence, we can say that ionization enthalpy, which is the amount of energy required to remove the outermost electron, is directly proportional to the penetration effect, and penetration effect is maximum in S orbital. So if we consider suppose 4s, 4p, 4d and 4f orbitals, then 4s electron will have highest amount of ionization enthalpy, even if all the 4 electrons they belong to fourth shell. They are at almost same distance or same average distance from the nucleus, but still due to penetration effect 4s electron will experience a greater nuclear force of attraction. The fifth factor which governs the ionization enthalpy is the electronic configuration of the atom. Now we know that half-filled and completely filled subshells, they are extra stable, and it is very difficult to remove electron from such configurations, because when an electron is removed from such configuration, the extra stability is lost. Hence, the electron or the atom is not in favor of losing such electron. Such configurations are ns2, np3, np6, nd5, nd10. If we see this, ns2 is a completely filled, np3 is a half filled configuration, np6 is a completely filled subshell, nd5 is a half filled subshell, and nd10 is again a completely filled subshell. So if such configurations are present, they are extra stable, and as a result the ionization enthalpy of such configurations is higher. We can say that ionization enthalpy is directly proportional to stability of the configuration. Now let us see how the ionization enthalpy varies in a periodic table. So let us see what happens to ionization enthalpy when we move across the period. Now when we move from left to right in a periodic table, following important changes they take place. The first one is the nuclear charge goes on increasing, and we know that the ionization enthalpy is directly proportional to nuclear charge. It means that the ionization enthalpy should increase when we move from left to right in a periodic table. The second factor which goes on changing is the atomic size. Now we know that atomic radius goes on decreasing from left to right in a periodic table, and also the ionization enthalpy is inversely proportional to atomic size. The third factor which goes on changing from left to right in a periodic table is the shielding effect, and there is a marginal increase in the shielding effect from left to right in a periodic table. However, we know that this shielding effect is affecting the ionization enthalpy in an inverse manner, that with increase in shielding effect, ionization enthalpy should go on decreasing. But the increase in shielding effect is marginal, because when we move from left to right in the same period, the electrons are added to the same shell. So there is no additional increase, or there is no addition to the number of shells, and hence shielding effect has very marginal effect. As a result, the overall effect is the synergistic effect of these two factors, the increase in nuclear charge and decrease in atomic size. Both of them lead to increase in the ionization enthalpy when we move from left to right in a periodic table. So in short, what we can summarize is, when we move from left to right in a particular period, the ionization enthalpy goes on increasing. Consider the example of second period. Now in second period, when we move from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, there is a continuous increase in the ionization enthalpy value or ionization potential value put here in this table in kilojoule per mole. For lithium it is 520 kilojoule per mole, to neon 2080 kilojoule per mole. So definitely there is an increasing trend. So if we plot this in a graphical manner, we'll find that there is a continuous increase. However, there are a few anomalies like beryllium and nitrogen. We can see three important things in this particular graph. The first is anomaly of beryllium. Now why? We can see that beryllium should have lower ionization enthalpy as compared to boron, because we are moving from beryllium to boron. It means that moving from left to right. In other words, boron should have higher ionization enthalpy than beryllium. But actually it is observed that beryllium has higher ionization enthalpy as compared to boron. Similarly, one more anomaly, that is nitrogen is having higher ionization enthalpy as compared to oxygen, and neon has exceptionally high ionization enthalpy as compared to all the other elements or overall trend of the IP in the second period. Now we will try to explain this on the basis of the one more factor which is governing the ionization enthalpy, that is the electronic configuration. Consider the electronic configuration of beryllium. It is 1s2, 2s2. So it has a 2s2 configuration where the valence shell is completely filled, and such completely filled shells are extra stable, and hence extra energy is required to remove the outermost electron from such extra stable configurations. Second atom, that is nitrogen, having atomic number 7, electronic configuration 1s2, 2s2, 2p3. Now this 2p3 is a half filled subshell where all the three electrons occupying one orbital each, and since there is a symmetrical distribution of the electrons, it is extra stable, and because of the extra stability, extra energy is required to remove the electron from outermost atom. So if we see or observe these two carefully, as compared to boron, beryllium requires more energy. As compared to oxygen, nitrogen requires more energy to remove the outermost electron. And neon has a configuration 1s2, 2s2, 2p6. Again 2p6 configuration is extra stable configuration with symmetrical distribution of the electrons, and hence neon has very high ionization potential value. Now let us see what is the variation of ionization enthalpy down the group. Now when we move from top to bottom down the group in a periodic table, again following three changes take place. The first thing, the nuclear charge goes on increasing. So nuclear charge will always increase whether we move from left to right or from top to bottom. Now we know that ionization enthalpy is directly proportional to nuclear charge. Second factor is atomic size goes on increasing due to addition of new shells when we move down the group. And we know that ionization enthalpy is inversely proportional to atomic size. And the third factor, the shielding effect increases substantially due to addition of extra shells, and there is an increase in the number of intervening electrons. Hence shielding effect is very pronounced, and we know that the ionization enthalpy is inversely proportional to shielding effect. Now if we observe this, due to increase in nuclear charge, it is expected that ionization enthalpy should go on increasing, but due to increase in the atomic size and shielding effect, it is expected that the ionization enthalpy should go on decreasing. And due to the synergistic effect of these two factors, the overall effect is decrease in the ionization enthalpy when we move from top to bottom in a group or down the group. This is the variation of ionization enthalpy down the group. So it is exactly opposite to the effect which is observed across the period from left to right. If we see this, the values of ionization potentials or ionization enthalpies in kilojoule per mole for the group 1 element from lithium to sodium to potassium to rubidium to cesium, we'll find that there is a continuous decrease of ionization potential values from lithium to cesium without any anomaly. So there is no exception at all. In short, we can summarize when we go from left to right in a periodic table across the period, the ionization enthalpy goes on increasing. When we move from top to bottom down the group, the ionization enthalpy goes on decreasing. The net effect of this is the lowest value of ionization enthalpy is observed somewhere over here in cesium, or in case of francium also we can say, but we do not generally consider francium because of the radioactivity of the element. But cesium is supposed to be the element with least value or lowest value of ionization enthalpy, whereas the highest values of ionization enthalpy are observed on the top right corner. So bottom left corner cesium, minimum ionization enthalpy, top right corner fluorine with maximum ionization enthalpy, with the exceptions of neon and helium. They are having exceptionally high ionization enthalpies since they are noble gases with noble gas configuration and completely filled shells. This is the overall trend of ionization enthalpy in the entire periodic table. This can be very clearly seen when we go from lithium to sodium to potassium to rubidium to cesium to francium. There is a continuous decrease. Same is the case with the noble gases also. When we move from helium to neon to argon to krypton to xenon to radon, there is a continuous decrease. So we consider any group, down the group there is a decrease in the ionization enthalpy, and in any period there is a continuous increase with a few anomalies because of the extra stability of certain electronic configuration. Such anomalies are observed in the second group, third group, fourth group, and so on. Now let us discuss the successive ionization enthalpies. We know that the energy required to remove the first electron is the first ionization enthalpy, energy required to remove the second electron is the second ionization enthalpy, and so on. Now the successive ionization enthalpies can be shown, like for example, if I have an element M, I supply an energy equal to first ionization enthalpy to remove the first electron, leading to formation of unipositively charged cation. When I want to remove one more electron, I will have to supply energy equal to E2, that is equal to second ionization enthalpy, to remove one more electron, forming a dipositive cation. The energy which is required to remove the third electron, which is equal to third ionization enthalpy, if I supply this much energy, one more electron is removed to form a tripositive cation. Now, in general, we can see that the energy required to remove the first electron will be minimum because the first electron is lost from the isolated gaseous atom. But when it comes to second ionization enthalpy, now the electron has to be removed from the positive ion. Now, since it is a positive ion, the nuclear force of attraction per electron is higher as compared to the isolated gaseous atom. Hence, more energy is required to remove the positively charged ion. Hence, E2 will be definitely higher than E1. Similarly, if I want to remove the third electron, now the ion is dipositive cation, already lacking 2 electrons. So nuclear force of attraction experienced per electron is much higher as compared to this. As a result, the energy required to remove the third electron will be still higher. So expected trend of E1, E2 and E3 is E1 lower than E2, lower than E3. Let us consider an example of two elements, lithium and beryllium. Now we can see that the first ionization enthalpy values of lithium and beryllium. Now we can see what is the trend. We are moving from lithium to beryllium, means we are moving from left to right in a periodic table in a period or across the period. Hence it is expected that the ionization enthalpy should go on increasing from lithium to beryllium, and this is observed in the first ionization enthalpy value, that the first ionization enthalpy of lithium is less, beryllium it is more, quite obvious. But when we move to second ionization potential or second ionization enthalpy, we find that the trend is opposite. The second ionization enthalpy of lithium is much higher as compared to beryllium. Now let us try to explain this on the basis of the electronic configuration. If we see the electronic configuration of lithium, we will find that lithium has electronic configuration 1s2, 2s1. So when we apply or supply first ionization enthalpy, it leads to formation of Li positive ion having configuration 1s2. And since 1s2 is a completely filled shell, the amount of energy required to remove the second electron to form Li dipositive ion will be much higher, and hence the value is 7298 kilojoule per mole. So E2 is much higher as compared to E1. Now if we consider beryllium, now beryllium has electronic configuration 1s2, 2s2. So if we remove first electron leading to formation of Be positive, one electron is lost and the electronic configuration is 1s2, 2s1. Now the second electron has to go from 2s1 configuration, and 2s1 is not an extra stable configuration. As a result, the energy required to remove the second electron is much less as compared to the energy required to remove the second electron from lithium, which is an extra stable configuration. And hence this type of anomaly is observed whenever there is a extra stable configuration in a particular ion. Now let us discuss some applications of ionization enthalpy. The first application is predicting the metallic character in the periodic table. Now we know that what is a metallic character? It is a tendency to release electrons. The tendency to release electron leads to a specific character to the elements, which we call as metallic character. And because of the tendency to lose electrons, the metals show their characteristic properties like luster, then the malleability, ductility, and there is a specific type of bonding called as the metallic bonding, which we will be discussing during the discussion in our next chapter or next module, that is the chemical bonding. So metallic character is due to metallic bonding, and metallic bonding is because of the ease of the atoms or the metal atoms to release the electrons. Now those atoms which will have lower ionization enthalpy will lose the electrons easily, and as a result they will behave as metals, whereas those atoms which are having higher ionization enthalpy will not release the electrons easily, and so they will behave as non-metals. So when we move across the periodic table, we know that the ionization energy or ionization enthalpy goes on increasing from left to right. As a result, the metallic character goes on decreasing from left to right. Exactly opposite is the effect down the group. So we can predict the metallic character on the basis of ionization enthalpy. Second application is application in predicting the type of bonding. Now, if we consider the elements which are present on the left hand side, they are typically metals. The elements on right hand side, they are typically non-metals. And the ionization enthalpy of these elements is very low. Ionization enthalpy of these elements are very high. Now, if there is a combination of these elements or any element among them in the pure form or in the form of a mixture, they will typically have a tendency to release the electrons, thereby leading to metallic type of bonding. For example, if you have sodium, potassium, calcium, so the atoms of these elements will have metallic bonding among themselves. Similarly, when we go on right hand side, the elements have very low tendency to release the electrons. As a result, if we have elements among themselves, will show a typical bonding called as the covalent bonding, because they do not have a tendency to release electron, but they have a tendency to share the electron pairs, and this leads to covalent type of bonding. But if we have one element or one atom from left hand side and one element from the right hand side of the periodic table, now these elements have a very strong tendency to lose electrons. These have very small tendency or negligible tendency to release electrons. On the contrary, they have a tendency to accept electrons. And if there is a combination of this element on left hand side and element on right hand side, a typical type of bonding called as ionic bonding will take place. So it is possible to predict the type of bonding present in the element on the basis of the ionization enthalpies. Third application is in predicting the number of valence electrons. If we see the first, second, third, fourth, etc. ionization enthalpies of various elements, they will have certain values. Now, on the basis of these values, we can predict how many electrons are present in the valence shell of that particular element. Consider the example of lithium. Now, if we see that the first ionization enthalpy of lithium is 520 kilojoule per mole, whereas the second ionization enthalpy is around 7298 kilojoule per mole. Now, this large difference is a clear indication that the first electron is lost very easily, whereas the second electron requires a lot of energy for its removal. This is clear from these values that after losing one electron, now the second electron has to go from the inner shell or from the stable electronic configuration. So we can predict the number of electrons in the valence shell that lithium has only one electron in the valence shell, because the second electron is going from the inner shell, leading to large increase in the ionization enthalpy. Similarly, we can see for beryllium, the second ionization enthalpy, first and second ionization enthalpy, there is a obvious increase from first ionization enthalpy to second ionization enthalpy, because the second electron is lost from the positive ion, whereas when we come to the third ionization enthalpy, there is a extremely high increase in the value. This clearly indicates that the third electron is lost from the inner shell, indicating that there are only 2 electrons in the valence shell. Similarly, we can have a few more examples like boron having third ionization enthalpy of some 3600, whereas the fourth ionization enthalpy is more than 25,000 kilojoule per mole, indicating that there are only 3 electrons in the valence shell. So in this manner, we can predict the number of valence electrons on the basis of the values of ionization enthalpies. Fourth application is in predicting the reducing power of an element. Now, what is an oxidation and what is a reduction, we will try to understand. Any reaction is called as a redox reaction because if it has a transfer of electron taking place from one species to another species. Consider an example, some element A and some element B, they are combining with a transfer of electron from A to B. This is called as a redox reaction because it involves reduction and oxidation. Always reduction and oxidation go hand in hand, because whenever there is a transfer of electron or whenever there is a loss of electron by one element, there is always a gain of electron by another element or another atom. Now in this case, if we split this reaction, we get 2 components from it. The first component is release of electron by this atom A. So A atom loses electron, get converted into cation. Now this particular reaction is called as a oxidation reaction because the oxidation number of A has been increased from 0 to +1 with a loss of electron. So this loss of electron is called as a oxidation process. And in this case, since this element A is losing one electron to some other species, the other species is getting reduced, and hence this element A can be classified as a reducing agent because it is reducing the other species which comes in contact with it. Similarly, B has a tendency to accept electron and get converted into anion B negative. Now, in this case, since B is accepting the electron, it is oxidizing the other species, thereby the reaction is reduction and the element B will be classified as an oxidizing agent. So if we consider this redox reaction, A is a reducing agent, B is an oxidizing agent, they are coming together, A is getting oxidized, B is getting reduced. Now what is the reducing power of an element? We know that if ionization enthalpy is low, then the element will have a very strong tendency to lose electron. And if it has a tendency to lose electron, it will act as a stronger reducing agent because it will give electron to the other species or other element. Thereby it will be stronger reducing agent. So the strength of the reducing agent is a function of the ionization enthalpy of the element. So stronger reducing agents are present on the extreme left of the periodic table because the elements on the left hand side of the periodic table have very low values of ionization enthalpy. Lithium is the strongest reducing agent in aqueous solution which is present on extreme left hand side, and reducing power is not only governed by this ionization enthalpy but also it is governed by the solvation and solvation energy. Lithium is the strongest reducing agent which is present on left hand side in the periodic table with low ionization enthalpy. Let us discuss now the fourth periodic property, that is the electron gain enthalpy. Now what is the electron gain enthalpy? Now we know that in case of ionization enthalpy we have seen that it is the amount of energy required to remove the electron, whereas electron gain enthalpy is defined as the energy released when an electron is added to isolated gaseous atom, and that is called as electron gain enthalpy, sometimes also called as electron affinity. Okay, and it is expressed in terms of kilojoule per mole. Again, most of the elements have a tendency to release energy when an electron is added, and since the energy is released, the process is said to be exothermic process and electron gain enthalpy is negative. Similar to ionization potential, this electron gain enthalpy can be classified as first, second, third electron gain enthalpy. So let us explain this, or let us visualize this in terms of a reaction. So you have an element X which is accepting one electron. So one electron is added to this X. This X is getting converted to X negative anion and some energy is released which is called as electron gain enthalpy. Now this electron gain enthalpy is related to electron affinity by a small variation, that electron gain enthalpy is equal to minus EA minus 5 by 2 RT. Now this value is the difference between these two. Most of the times we use the word electron gain enthalpy and electron affinity by the same meaning, with the same meaning. However, there is a very small difference between the two. Now similar to ionization enthalpy, there can be first electron gain enthalpy, second electron gain enthalpy. However, the problem of second electron gain enthalpy is that first electron gain enthalpy is always negative because the energy is released, but the second electron gain enthalpy is always positive because electron has to overcome the repulsive force of the anion. For example, if I want to add one electron, the first electron is added to isolated gaseous atom, and since it is added to atom, energy is released. So this energy or this enthalpy is negative. But if I want to add one more electron to this, there will be repulsion between the two negative charges, one of the anion which is formed over here, and plus second the electron which I want to add to this particular ion. And for that I will have to supply energy to form this di-negative anion, and as a result the second electron gain enthalpy is always the energy supplied, and so it is always positive. Okay, now let us see what are the factors which govern electron gain enthalpy. The first factor which governs the electron gain enthalpy is the atomic size. The second one is the nuclear charge, and third one is the electronic configuration. We'll try to explain all these factors in details. The first factor is the atomic size. Now, consider an atom having some specific size and an electron is to be added to this particular atom. When an electron is added, there is always a force of attraction between the nucleus and the incoming electron. Now this force of attraction is proportional to the nuclear charge or the charges on the two species, and it is inversely proportional to the distance between the two. As a result, if the atom is smaller, there will be a larger force of attraction because the distance between the incoming electron and the nucleus is less. But if the atom is larger, in that case, the distance between the nucleus and the incoming electron is larger. And since the distance is larger, there will be less force of attraction between the two. And as a result, whenever the electron is added, less energy is released. In other words, if the atomic size is small, more energy is released. If the atomic size is large, less energy is released. Or we can say that the electron gain enthalpy is inversely proportional to atomic size. Smaller atom, more electron gain enthalpy. Larger atom, less electron gain enthalpy. Second factor is the nuclear charge. Now, consider a nucleus with higher positive charge. Now, if we want to add one electron to it, there will be larger force of attraction between the incoming electron and a higher positive charge of the nucleus. So, when this electron is added to the atom, larger amount of energy is released, or the electron gain enthalpy is larger. When I say that it is larger electron gain enthalpy, I am talking about more negative value of electron gain enthalpy. But if the positive charge on the nucleus or nuclear charge is less, then the force of attraction between the nucleus and the incoming electron is less, and as a result, when this electron is added, less amount of energy is released and electron gain enthalpy is low or lower negative. In other words, we can say that the electron gain enthalpy is directly proportional to nuclear charge. More is the nuclear charge, more is the electron gain enthalpy. The third factor which governs electron gain enthalpy is the electronic configuration. Now we know that half filled and completely filled subshells are extra stable, and if an atom is having such type of extra stable configuration, it will have negligible tendency to accept additional electron, and hence there will be very low electron gain enthalpy, or sometimes even the positive electron gain enthalpy. Such configurations are NS2, NP3, NP6, ND5, ND10, etc. So in other words, we can say that the electron gain enthalpy is inversely proportional to stability of the configuration. If the configuration is already stable, the element will not have, or the atom will not have a tendency to accept the electron. As a result, electron gain enthalpy will be either 0, or in sometimes it will be even positive. Let us see how the electron gain enthalpy varies across the period and down the group in the periodic table, one by one. So now when we move across the period from left to right, certain variations take place. The first variation is nuclear charge continuously go on increasing because of the increase in the atomic number from left to right. As a result, now we know that electron gain enthalpy is directly proportional to nuclear charge. So electron gain enthalpy should go on increasing. Second factor is the atomic size, which goes on decreasing from left to right in the period. And we know that electron gain enthalpy is inversely proportional to atomic size. As a result, again this factor favors reduction in the increase in the electron gain enthalpy because of the reduction in the atomic size. So the combined effect of both the factors is that there is a continuous increase in the electron gain enthalpy from left to right across the period. So this is obvious. Now let us take an example. If I have the second group elements, when we move from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, this is the variation of electron gain enthalpy in kilojoule per mole. Now we will see that there is no clear trend if we just observe the values. However, if we plot it, we will find that from lithium to fluorine, it is expected that there should be a continuous increase in the values of electron gain enthalpy. However, we will find that for beryllium, for nitrogen and for neon, the values of electron gain enthalpy are positive, whereas for all other elements the values are negative. This can be explained on the basis of the electronic configurations of these elements. Let us see one by one. The first element showing the anomaly is beryllium. Now, beryllium has 1s2 2s2 configuration, and since the 2s orbital or second shell is completely filled, or the 2s subshell is completely filled with 2 electrons, it will have negligible tendency, or even it will oppose the addition of electron to this element, which reduces its stability. For nitrogen, the valence shell configuration is 2s2 2p3. Now in 2s2 2p3, now this 2p3 is extra stable configuration. Addition of one more electron leads to decrease in its stability. Hence, nitrogen has got a slightly positive value of electron gain enthalpy. So it will not accept the incoming electron easily. Same is the case with neon, which is having extra stable configuration of 2p6. Also it is a noble gas with completely filled second shell, so it will have negligible tendency to accept the electron. Thereby the value of electron gain enthalpy is positive. When we say that the electron gain enthalpy values are positive, it means that we will have to supply the energy if we want to add an electron to these atoms. Coming to the variation of electron gain enthalpy down the group. So when we move from top to bottom down the group, again certain variations take place. The first variation is the change in nuclear charge, which goes on increasing continuously. And since the nuclear charge is increasing, it is expected that electron gain enthalpy should go on increasing. However, at the same time, the atomic size goes on increasing down the group, and we know that atomic size has a inverse effect on electron gain enthalpy. Hence, one factor is favoring the increase in the electron gain enthalpy, whereas the second factor is favoring the decrease in the electron gain enthalpy. The overall effect is the predominant effect of large increase in atomic size down the group due to addition of extra shells. And as a result, since there is a large increase in atomic size, the net effect is a reduction in the electron gain enthalpy down the group in a periodic table. So, if we consider an example of first group elements from hydrogen to lithium to sodium to potassium to rubidium to cesium, we'll find that the electron gain enthalpy values continuously go on decreasing. When I say decreasing, they are the negative values getting decreased. It means that the tendency to accept the electron goes on decreasing. This is a clear trend without any anomalies from hydrogen to cesium, continuous decrease in the electron gain enthalpy values. Now there is an anomaly in case of the halogen elements. We can see that for chlorine, bromine and iodine, there is a continuous decrease in the values of electron gain enthalpy, but fluorine has got some different value than expected. This can be shown graphically by this particular graph. Now we can see that from fluorine to chlorine, actually it is expected that if we extrapolate this iodine, bromine, chlorine values, it is expected that fluorine should have the electron gain enthalpy higher than chlorine somewhere over here. However, it is observed that there is a decrease in the electron gain enthalpy for fluorine. Now this can be explained on the basis of two factors. The first factor, if we consider the electronic configuration of fluorine and chlorine. Now fluorine has only two shells with electronic configuration 1s2, 2s2, 2p5. When one electron is added to this particular shell, we will find that this shell will have a capacity or will have a complete accommodation of 8 electrons. Now, since this is a second shell, its capacity is of 8 electrons and it will gain 8 electrons when one electron is added to fluorine. Hence, it will be full to its capacity. But in case of chlorine, the valence shell is the third shell, and third shell has a capacity of 18 electrons. And when we add one electron to this shell, it will get 8 electrons. Now, since the capacity is of 18, it is having only 8 electrons, and hence it is not completely filled, but it is partially filled. Now this is completely filled second shell. This is partially filled third shell. Now since this is a completely filled second shell, the interelectronic repulsion is very high in case of fluoride ion, and interelectronic repulsion is much less in case of chloride ion. And in order to overcome the interelectronic repulsion, there will be decrease in its stability, and as a result the fluorine will have lower electron gain enthalpy as compared to chlorine. Secondly, the atomic size of fluorine is much smaller as compared to chlorine, and as a result the repulsion of the electrons is much higher. And since there is a large repulsion among the electrons in case of fluorine, the fluoride ion has got, or the fluorine atom has got, a lower value of electron gain enthalpy as compared to chlorine. So we can explain this particular behavior of fluorine on two grounds. One, the capacity of the valence shell, and second, the atomic size. Now we know that fluorine is the smallest atom in the periodic table after hydrogen, because we know that the smallest atom lies on top right corner, which is our fluorine atom. So this is the explanation of our abnormal behavior of this fluorine. In short, we can summarize this increasing electron gain enthalpy across the period from left to right and decreasing electron gain enthalpy from top to bottom down the group. Because of this, the highest electron gain enthalpy should have been with fluorine, but it is actually with chlorine because of the size effect and interelectronic repulsion effect, and we have negligible electron gain enthalpies for neon and helium because of the noble gas configuration. So highest value of electron gain enthalpy in the entire period in the entire periodic table is chlorine, and lowest values with helium and neon. Argon also. Coming to the overall trend of electron gain enthalpies. Now we can see there is no clear cut trend, or there is no sequential trend because of the anomalous behavior or extra stable behavior of certain configurations in helium, beryllium, nitrogen, neon, magnesium, argon, which are having extra stable configuration. They have 0 or positive values of electron gain enthalpies, whereas the other elements have negative values of electron gain enthalpies with slight variations, but the variations are not in a trendy manner if we compare it with the other parameters or other periodic properties like atomic size or screening effect or the ionization enthalpies. This is all about in this particular lecture number 2 on periodic properties. We will continue the remaining periodic properties in our lecture number 3. Thank you. Thank you very much.